All right, hello everyone, and welcome to Handmade Hero, the show where we code a complete game live on stream. Today we are going to talk about shaders because we need to put shaders into the game for possibly some effects reasons. Obviously, we might want to do some things with lighting in the future that would require us to have a shader in there. But the more pressing need and the reason that we're doing them at the immediate moment is just because we have to do some modification of the Z values that are used for Z buffering in the game. And I am pretty sure that the most efficient way to support that, rather than monkeying with vertices when they are output at runtime, is actually instead to, in the shader, take an additional coordinate that will allow the shader to go ahead and tweak the resulting Z values after the transform. That, I think, will be the most efficient thing for us to do. We will see in a second if that's actually true or not, but I'm pretty sure it is. So in order to get there, though, I've got to explain a bunch of stuff. So hopefully we can get through that in a relatively short amount of time. And then we can move on to actually trying to get one of the shaders working in-game to basically just replicate the pipeline we have now with shaders. And then we don't have to get all the way to fixing the Z part, because that we can do the following week if we want to. But let's go ahead and open up Milton here. All right. So today is day 369. Feels like my tablet is not pressure recognized for some reason. Where is it? There it is. Yeah. All right. So let's see. Day 369. So let's talk about shaders. I've mentioned these in the past, and we should go ahead and give just sort of a brief recap. In order to understand shaders, the very most important thing is that you understand how renderers work in general. And so the number one thing you should do, if you aren't comfortable with it or didn't watch it, is go back and watch the implementation of the software renderer, both the implementation of the rotation part and the implementation of the optimization part, because that is crucial to understanding how shaders work. That is 100% what you need to understand how shaders work. If you don't understand that stuff very well, go back there first. Don't even bother watching this episode. Because that is the crucial thing to understand first. So I'm going to briefly say why that is, just so you can map the knowledge on, and then we'll talk about the shader-specific stuff. So the way hardware, in most cases, on the PC, does pixel processing is that the pixels themselves are treated as a block. So if you recall, the way our software renderer worked is we took 4 pixels in a row that were packed RGBA. So it was, RGBA, 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 or I think in our case, we actually, because of the Windows format, we were doing BGRA, BGRA, right? But point being, we had 4 packed pixels, each of which had 8 bytes per channel of RGB and A, which is 32 bits. So we had 4 32-bit pixels, or 4 by 32 here, which is 128 bits, right? 4 32-bit slots, if you will. So if you imagine what that looks like, you can imagine those pixels here. Here's pixel 0, 1, 2, 3, and there you go, right? Now, in graphics hardware, there is obviously no particular, so if you imagine what a typical graphics primitive looks like, a triangle or something like this that we're going to want to treat individually to rasterize, right, to produce the pixels for a particular triangle, obviously there's no particular bias towards them looking like long and slivery like that, right, or like this. typically triangles are more like this shape, right? They're more like reasonably sized in most cases. If typically artwork is trying to, if it can, distribute the triangle load evenly over the artwork so it gets good coverage. So typically they're more reasonable in terms of their area. They're more even in terms of their area and not extremely long and eccentric. So what I would say is if you look at these pixels in a row here, the fact that we were treating our pixels in a row like this sort of suggests this style of triangle, right? A more sensible way, potentially, if you could control everything about it, would be instead to have arranged our pixels like this, right? Because now we maximize the chance for a triangle that all of the pixels fall inside. Whereas in this case, right, we are sort of maximizing the chances that they don't, because we're creating the longest possible run in one dimension, right? Which isn't very good at keeping things inside uniform size shapes. Now, the reason we did that was just because in terms of how we load in memory, and because we're required to output things in a certain way to Windows, that just made the most sense. We needed to use SIMD, right, which is SIMD single instruction multiple data, right? We needed to use the SSE streaming SIMD extensions on the Intel architecture to do fast processing of pixels, and that is 4 wide at a minimum, right? The version we were targeting is 4 wide. It does operations on 4 things at once in floating point, and so we wanted to be able to load something that was 128 bits, blow it out into channels and do 4 wide ops on them. And of course, when you're doing the operations, you're doing operations specifically for red channel, green channel, blue channel. So you want 4 reds, 4 greens, 4 blues, and 4 alphas, right, in order to fill your entire SIMD width, right? Now, all of that stuff, if that sounds unfamiliar to you, you have to go back and watch those. I'm not going to explain that again here. You have to know that stuff. So go back and make sure you've got your fundamentals of software rendering first so that you'll understand what we're talking about with shaders. Okay. So yes, this square, much better pattern for keeping things on average inside uniformly shaped things. So the way that graphics cards actually process things is they do process them in squares. Now it depends on the card itself necessarily, right? It's not always the same. But basically what you get is you get an extension of the size of things being processed into something more like this. And this is not exact. Like I said, every graphics card can be different depending on the architecture, AMD versus NVIDIA, how wide it is, these sorts of things. But this is an example of what it might be, 16 pixels at a time, right? And so what it does is it creates a square. It still does load 4 pixels in a row, but it also loads basically 4 rows of that. So it's 4 by 4, again, in a square pattern, especially when you get to this size. You can imagine if we did 16 pixels across, there'd almost be no chance that most of those would fall inside the same triangle. So they tend to try to put it into more geometrically reasonable spaces, right? So it's going to load 16 pixels at a time, let's say. Some, I think, only load 8. I don't know the exact breakdowns of which cards do what or how that goes. You'd have to talk to more of a GPU expert for those sorts of nitty-gritty details. There's also things like pixel packing, which try to gather pixels in. And there's all sorts of shenanigans that happen on GPUs. So this is, again, just the high-level overview. I'm not trying to say this is exactly how a GPU is going to function, because it's not. So you have to imagine, when you start thinking about shaders, that when I'm going to start filling pixels, I'm going to do them in exactly the same way we did in our software rasterizer, only I'm probably going to do it much wider. So instead of a 4-wide SIMD, think 8-wide or 16-wide SIMD, so much wider, which means we want to gather up a good chunk of pixels, either 8 or 16, to do all our operations on, and when we're going to do those operations. Just like our system, they are masked. So if the triangle passed through in this way, then you're going to get a mask which says, well, all of these pixels are filled, but these two weren't, right? And that mask is going to say how to write back the results. So it won't affect, even though it computed 3 and 12, it won't affect 3 and 12, right? This is also sometimes colloquially called a warp in NVIDIA parlance. When you're looking at like CUDA or something, they talk about the number of things being processed together. I just think of it as SIMD again. I just think of it as the register width or the operation width. But the things that travel together like this, where we're processing all the pixels together, they call a warp for some reason. I don't know why. They probably have a reason, but I don't know what it is. That might come, I don't know, warp might come from some multiprocessing literature like earlier on. I'm not sure. Anyway, so fundamentally speaking, when we are talking about writing a pixel shader, what we are writing, even though it doesn't look like it when we write it, what we are writing is 100% just the exact same kind of code that we were writing when we wrote the software rasterizer. When you're writing a shader, it is literally the exact same process. You should be thinking exactly the same way as you are thinking when you write a SIMD software rasterizer, which is why, having done that, you're in much better position to understand how to write a shader. And if you haven't done that, you're going to be kind of confused. So why do I say that? Well, when you write a shader, what you're going to see in the shader is you're going to see code that looks a lot like C code, and it won't look very much like SIMD code. In the shader, you'll see things like, okay, I have a vec4, and the vec4 is maybe like the texture sample, right? And I will call something like texture 2D. And I will pass it, some UV coordinates. Well, I'll pass it, the texture to sample and the U and V or something like this, right? So you'll see code that looks a lot like this. It will have built-in types, and those built-in types will be types that are defined by the OpenGL shader compiler. So vec4 is basically equivalent to our v4, right? It's a bundle of 4 floating point values. You declare variables. They're variables just like you would think of them in C, which are like text sample or whatever. You give them a name and they correspond. They have a type. You will see assignment, and you'll see built-in functions. So this is a function specified by OpenGL that does texture sampling. You pass it some parameters so it knows what it's going to do. This texture, this U, and this V we'll have to get from somewhere, right? And the textures are usually abstract. They're not pointers directly a lot of the times. Because we don't have access to the pointers at that kind of a level. So you can use extensions and actually do some stuff like that with like NVIDIA extensions and stuff, but we're not going to talk too much about that because that hasn't really made it into the mainstream as much yet. Although the 4.5 ARB stuff, I think, actually does let you do that. I don't think all the binding stuff did. That's a rat hole we can talk about at some future date after we get the basics down. Not important right now. Anyway, this is the sort of code you will see. But the important thing to understand when we're writing this is that any time that we're seeing things that are happening here, all of these things are times 16. So even though we aren't going to write anything other than what happens for a single pixel, so this is like an example of instruction that would happen for a single pixel, right? Here's the texture, here's the UV, we're sampling a texture, we're getting back an RGB vec4 that says here's what the color is, right? So we're looking at it and we're typing it in and it seems like it's just a single pixel. It's not. It's 16 pixels or some number of pixels that are having this happen, right? So you have to understand that basically all of these things that you're writing in are effectively as if you were doing the wide version. So then when you then say text sample, right? Down here, and you're like, oh, I want to times equal that by 4.0 to, like, I don't know, make it be, and I don't think you put Fs on anything in shaders until later. They added the ability to do that, but originally you didn't do that. If you do text sample times equals 4.0 to multiply all of the members of that by 4, let's say, this is actually the equivalent of doing something like what we were doing before, where we had the right? Mul PS stuff, and we said, okay, we've got the, oops, I think that's just underscore mul PS. We write something like that, and we just say, okay, we've got the text sample and the set1 PS 4.0. So if you remember how we wrote that code, this is basically equivalent to that. So every time in a shader you write a basic operation that looks like a scalar operation in C, it's actually expanding it out to a SIMD operation that's going to operate on many things at once. You don't know how many, because the graphics card is free to choose. Like some graphics cards are 16:8 wide, whatever. They could be 32 wide, who knows? Whatever the manufacturer wanted. So you have to understand that that's what's happening. Now, the reason it's important to understand why, understand that, and to understand the fact that these things are getting blown out to the width, is because what that means is when you think about the peak throughput of the sampler, when you think about how much performance it's going to get, it's going to be based entirely on how much of this number you can leverage, right? If you are constantly filling all 16 pixels and using them, and all of the instructions for all 16 pixels are getting used, then you are going to get close to doing the number of gigaflops that that card is capable of doing. You're going to be using the floating point capabilities of that card to the fullest extent that you can. However, if you don't do that, then you could go anywhere from slight degradation in performance to drastic degradations in performance, as much as like 1/16 the performance, or who knows, even less, right? And how that happens is if you write shader code unaware of what is actually going to happen under the hood. This is pretty harmless. This will only get nixed on the 16 when the triangle itself doesn't cover enough pixels, right? So when you're doing something like this, and you've got 16 there, and only these fraction of them are in, then you're not going to get that 16, right? And so there's always some loss, and that loss, it could even be half, who knows how much it is. But there's always going to be some loss just due to the fact that you can't always get enough pixels actually relevant into the shader, right? And that's the fault of the geometry, and that's something you do have to be aware of when you're thinking about how to make sure your geometry is nicely even and does reasonable filling and that sort of stuff, right? And remember, this gets better once you start thinking about MSAA, right? Because with multi-sample anti-aliasing, this 16 wide, well, if you did 16x oversampling, like let's say you did 16x MSAA, then this 16 wide is all inside a single pixel, right? So, it gets better with the more multi-sample anti-aliasing you have, because then you're less and less likely to have triangles missing things. So there's that as well. But anyway, so you start off and you assume you've got some lossage due to coverage, which you can't really control as much. The more multi-sample anti-aliasing you have, probably the less of that you have to worry about, because you have less and less pixels per warp, and just, a lot of those are samples that are inside the same pixel, so that's good. But and again, even those samples, though, can still be outside, I guess is the other way to think of it too, right? So if you're right on the edge of the triangle, then you can still have the samples outside, just like you have pixels outside. But I guess what I'm trying to say is multi-sample anti-aliasing it increases your effective resolution by up to 4x4, right? At which point you're just much more likely to have triangles of the same size cover more of your samples, right? That's all. It's just like increasing the resolution. Decreases the sizes of a 4x4. If the triangles stay the same size, they're going to cover more of them, right? So anyway, when we go through this, we have some losses due to geometry. That's understandable. And that's not your fault in the fragment shader. It may be your fault for how you set up the geometry, but that's a separate issue. Once you get into the shader proper, you can lose a lot of that parallelism by not thinking through what things cost. So for example, in a shader, you can write an if. I could say, for example, if the text samples, right, and the vec4s work very similar to how we wrote them in our C code. So you can say, for example, .r to get the red channel out of a vec4. So I say if a text sample red for, is not equal to 0, let's say, then I'm going to do some code here, and then I'll do an else branch and say, well, if it was equal to 0, I'll do something else, right? So you can write these sorts of things in a shader. Similarly, you can write for I loops or something, right? I could write a for loop here. I could say, for, I don't know, or a while loop, like while, text sample r is greater than 0. And we just go through here, and at the end of this, I do like r, text sample r minus equals 0.1, right? So shaders let you write complex flow control just like you could write in C. You can call functions, you can do if statements, you can do while loops, but like I said, it's crucial to understand. If you just look at that and you don't understand how SIMD code works, you're going to be very confused as to why your performance is what it is. So what happens when you write these things is just like we wrote them for our masks, for our write masks in the shader, in the software rasterizer code that we wrote. Just like that, all the branches of a loop and all the branches of an if and all of the iterations of a loop have to happen for everybody always. Because remember, there's just one processing unit responsible for executing this code for all 16 pixels at a time, or 16 samples at a time, right? There are multiple cores on a GPU, but in terms of one set of 16 pixels flowing through that pipe, or 8, or however wide it is, just like SIMD, there's only one core doing it. So you can't branch uniquely per sample. You have to branch one way for all 16 samples. So what ends up happening is when you do an if and you look at textsample.r is not equal to 0, it's going to do the same kind of early out that we might do in the software rasterizer. They might do a check to say, are all of the texture sample.r's not equal to 0? If they are, then it will just execute this branch and not this one. If they definitely are not, if they all are not, it could execute just this branch and not this one, right? But most of the time, probably, and again, this is just something you need to be aware of, if you know that that's the case, like it's always all zeros or it's always all not zeros, then you're probably fine performance-wise here because you haven't introduced a problem. But assuming it can be a mixture, then you are going to execute both branches. Both branches will always be executed, right? And what will happen is it will create a mask. This instruction will actually do a comparison and take the mask, and it'll leave that mask in a register. It will then execute all of these instructions and all of these instructions, and then it will combine them using the mask into the result. So all of the pixels in the warp that had the red channel not equal to 0 will get these results fused in to their slots, and all of the ones that didn't will have it fused in, will have what happened here fused in, right? So this produces one result, whatever it is, this produces another, and then they get masked together, right, into the result. So again, understanding the shader, just knowing what it does, you can read this just like scalar code, and yes, that's fine. But understanding how it performs and works, it's crucial for you to understand that depending on the architecture of the GPU, there can be very serious performance concerns to things like if statements or loops if you don't understand what you're actually asking the processor to do. If you think that you're just asking it to do one or the other, you're wrong. That's not actually what it oftentimes will have to do. So that's just worth understanding. And again, this multiplier is big. Getting 16 times the performance out of something from SIMD is no laughing matter, right? Take how fast your graphics card is, divide it by 16, right? That means if its max frame rate was 60 frames a second, you're talking about dividing it by 16, you're going down to something that wouldn't even be playable, right? You're going down to something in the like 2-3 frames a second, something like that, right? So you have to understand that every time you start shaving off some of that performance, you're hurting yourself in terms of getting what you need out of the graphics card. So you can't just willy-nilly write things that'll like do things to just 1 or 2 pixels all the time and they'd all get fused together in this giant shader. It'll cost you, right? The same is true for loops. Loops are just ifs and jumps, right? That's all they are. They're just like I'm going to do a comparison and say if this thing is true or not true, I'm going to jump one way or the other depending on it. Either I'm going to I'm going to let it fall out of the loop or I'm going to jump back to the top of it. So the same thing happens here. However many times through this while loop the longest pixel goes, that's how many everyone goes. So even if you're on average, all of your pixels like only take 1 or 2 loops, let's say, right? But in every warp of 16, there happens to be one that goes like 300 loops, then every time it will be doing 300 loops, right? Now, it's probably not going to happen that way. It's probably going to be that only a few, of those warps will have the 300 loop case. But again, every time you hit the 300 loop case, you're doing that 300 loop for all 16 samples, not just that one. So you lose the performance on everyone in the warp when that happens. And that's very important to understand, right? So that's the thing to keep in your mind when you're writing shaders, is that you are wide, and everything you do is going to be interpreted as SIMD-style instructions. So just keep that in mind as we're writing it, and you'll be much, much better off in terms of understanding the performance. On Handmade Hero, we don't have a lot of complex things that we need to do in the shader, so we probably won't have to keep this in mind for ourselves very much. We will not be pushing the graphics card's shader capabilities in any real way. So I won't have a chance to really show you this in action, but when you are doing more complicated engine work where you're trying to do photorealistic rendering or who knows what else you're doing, gather indirect lighting, who knows, that sort of stuff. This is the sort of thing that you have to understand. It's going to be important for you to get it right. Okay. So now the only other thing that we need to talk about before we can go write some shader stuff is that there's 2 parts to the shader pipeline, one of which we haven't really mentioned yet, and the other is the part that we just talked about. So that part I just talked about in OpenGL parlance is called the Fragment shader, right? There we go. Let's try that one more time. Fragment. But we also need a thing called a Vertex shader. And what a Vertex shader does is a Vertex shader is basically the transform stuff that we have done in our graphics pipeline to do that perspective transform and anything else that you want to do that happens per vertex. So in OpenGL, right, we're sending down these vertices, X, Y, Z, W, X, Y, Z, W, etc., right? We're sending down these vertices to the graphics card, and then we just talked about, okay, then somewhere over here, the graphics card is going to have this warp of pixels, and it's going to fill, or samples, pixels. In our case now it's samples because we're doing MSAA. So it's going to have this warp of samples. Those samples are going to be computed. And so obviously somehow we got from here to here. And that's where the vertex shader part comes in. There's also other things called tessellation and geometry shaders, which can happen before the vertex shader stage if you want to do more complex work on these vertices. This is essentially the like one in, one out pipeline, right? You put in, say, 3 vertices for a triangle. You get out 3 vertices that get rasterized into a triangle for fragment shading. But there's other ways you can do, say, if you want to just put in one vertex and have that blow out to hundreds of vertices that got interpreted as triangles or something like that. So for amplification, that sort of thing. If you want to do stuff like that, there are shaders that can do those sorts of things as well. They happen before they happen back here, right there. Ooh. Having a lot of Milton problems here. What's going on? There we go. So there's stuff that happens to the left of this diagram that we don't need to worry about right now. But for our purposes, we do need to know about these two. So a vertex shader is exactly the same kind of code as a pixel shader. There's almost no difference between the two of them. The only difference is instead of working on, say, 16 warp, a 16 size warp of fragments or samples or pixels, instead we're going to do a 16x warp of vertices. So instead of taking in fragments, we're just going to take in like 16x's, 16y's, 16z's, 16w's into our vertex shader, and we're going to operate on them, right? All the same stuff I just said applies. In fact, it does not. You don't even have to think in either shader about anything different at all, really. They're both pretty much exactly the same in almost all respects, except for some things like fragment discard and stuff that we'll kind of touch on a little bit maybe later. But basically exactly the same. It's just taking a big old batch of scalar values, 16x's, 16y's, 16z's, 16w's, 16 anything else, colors, 16 UVs for your textures, 16 whatevers, right? Transforming those and preparing them to be output to the fragment shader. So what we will do is we will say, when we declare these, and you'll see me do it, we'll say what travels across this boundary. You know, probably the positions for the vertices of the triangles that are going to get rasterized, probably the texture coordinates that are going to be used to look at the textures, probably a color value for doing that modulation, right? So we're going to declare the stuff that goes across, and we'll make them line up. But basically, all that's going to happen in here, there's nothing special at all. It's just doing the bulk work of taking in raw vertices from the app streams that we define and sending them over to the fragment shader processed so that it can start doing rasterization on them, right? Now again, there actually is a rasterizer in here, right, that we don't see. And that's the thing that takes an actual triangle and generates the pixels that are or samples that are actually used in the fragment shader. That is not programmable. So the vertex shader outputs the vertices that will be used to rasterize the triangles. The fragment shader takes in the fragments that triangle covers, right? But in between there is the rasterization step, and you don't see that. So you don't get to see how triangles are rasterized or change it. That may change in the future, but for right now, it's not. That's just what it is. OK. So that is the end of that. Let's go ahead now and actually do some work with these so that we can see how this works in practice now that you get the idea about how they work. And again, this is day 369, so start with day 368 source code, and that's what I'm going to be starting with now. So here's on the OpenGL side of things. If you remember correctly, we started with our, let's see here. Here we go. First thing I want to do is actually correct something that Martin's pointed out. One of the problems with programming OpenGL on stream is I don't have time to really read the docs much. And OpenGL I don't tend to know by heart, just because I don't tend to really love graphics APIs, if you couldn't tell. So I usually just make my own, and then I kind of just write a little binding layer and read the docs for a few weeks to get the right stuff. But I tend to not think in terms of OpenGL or anything like that. So I sometimes make errors in the minutia. And in this case, Martin's pointed out that looking at the validate status to get compile errors isn't necessary and perhaps not wanted, because validation, what it does is it checks the entire state of a program, including whether or not things like the arrays that are bound at the time to take vertices are compliant with that vertex shader and stuff like that. we didn't want any of that sort of thing. We didn't want a full validation. So really all we need to do here when we check the status is we really just wanted the link and compile status. So we can get the link status and compile status like so. And so what we can do is say, link validated, compile validated. We'll just do linked and compiled. And then we've got a way to check, like, OK, if we linked and compiled or if we didn't. So I'm just going to go ahead and grab those in just to make that, because that's I don't want to leave that in sort of a not quite the right way to do it state. So let me just go ahead and get core arb out here. Oops. And I'm going to grab those guys. All right. And we'll leave validate stats in there because we may want to do validation later on, so we probably want to keep that going. All right, so now in theory, if we run this, we should be able to still get compile errors on it, which is what we wanted. Here's that shader validation failed, and if we look, we get the logs that we wanted, which is what we were doing before. So what we want to do now is we want to actually start doing some of these shaders. We want to try to compile a shader. Martin's also pointed out that that in Visual Studio 2013, which is the version we are using on Handmade Hero, you can use the multi-line strings. It does have that support as in 2013, apparently. I've never tried it, but he said you can. And what that means is that we could do something that allowed, well, here, I'll bring it up. Do we have a... So this one right here is the one we're talking about. I don't know if the here doc stuff. Yeah, you can ignore the rest of this for now. But you can see here how this stuff works, where you can say, OK, you've got this R prefix where you're basically saying, hey, this is going to be a string, because I don't know if you remember, I don't remember if we ever did wide strings. I don't know that we ever actually did that. But in C++, you can prefix, for example, a string with an L, and the L prefix means that it's going to be a UTF-16 string, right? And you can see some other things in here where they've got some other prefixes, right? But basically what this is something that comes before the quote, that will tell you that will tell the C compiler this is a special kind of string. And this kind of string is basically a way of saying, hey, I'm going to put a delimiter in here that's going to tell you when you can end. And so there's going to be a delimiter followed by an open parentheses, and then close parentheses, and then another delimiter. And I'm going to guarantee to you that that delimiter will never appear anywhere in here. So basically, I'm going to give you the way of telling when you've got to the end. And that, again, is, we talked about this as the here doc support. I didn't think that that was in 2013 yet, but Martin says it is. So that's good if we can do it, because that means we could make our shaders pretty conveniently, right? That means we could do something like this. And then close it like this. And then we don't actually have to do anything bizarre. In theory, anyway, if it worked. Now, I don't know if it will, but that's this. Yep, and it does. So I guess we can actually use those here docs, which is awesome. It also means we can write our shaders and include them in line if we'd like to. So we could write them as separate files if we want them to be separate files. But we can sort of cross that bridge when we get a little further down the road. So let's go ahead and try this here. Oops. I don't know when they added this, but it's nice that they did. I wonder if it's in 2012. I don't know when I don't know when it made it in there. Anyway. Oops, don't need that. So, if we take a look at how that works, I guess there's really probably not a lot of, I'm assuming that pound includes in here would not be parsed. So we would still, even if we wanted to write a file that had the shader in it, we'd probably still have to put the R colon in front of it, I would guess. But, that's probably okay. So it's still not quite ideal for our purposes, I guess. But nothing you can do about it. All right. So here we go. Here's our header code, here's our vertex code, and here's our fragment code. And essentially what we need to do now is we need to sort of learn the structural syntax of these shaders so that you can do useful stuff with them. And one of the things that typically helps, if you can find it, and we'll have to talk about the versioning a little bit here, but if you can find it, is this shader language is called GLSL, right? The GL shading language. And if you use that GLSL search term and look for a GLSL like version, like 1.3 quick reference card, hopefully you can find one. Here we go. I think 130 is the version number for whatever reason on OpenGL shader language 3.2. I think maybe, I can't quite remember what the version numbering is. The version numbering on these is really weird. That's the reason I typed in 1.3. You don't put #320 to do a shader in this one. You do #130, and you'll see that in a second. If it sounds like I'm babbling about it, let me take a look here. GLSL version directive. So it's this thing. Basically what happens here is you can kind of take a look and see like, okay, so if I want to select a shader version that's going to be backwards compatible to sort of older things, you can go back to say OpenGL 3.0 or 3.2 and pick out one of the version numbers. And unfortunately, the version numbers don't correspond with the OpenGL versions because reasons. So typically what ends up happening is you have to pick a version of the language to say what to your shader, because the shader does get the shader versions are not backwards compatible with each other. So you have to pick a version that you're going to use. And once you pick that version, the first thing you have to do inside the shader code is say what version it is that you think you're actually trying to use, so that you can guarantee that the compiler will know what you were looking for, right? So in our case, we can probably get away, since we're not really doing much of anything in the shader at this point, we can probably get away with just using shader 3.0, let's say. So a #130 version would be fine. And so what we can do here is just say, all right, give us shader version 130, okay? And in theory, that should work just fine. Oops, I don't need to put that in all of them. I can just put that in the shared header. So in theory, that should be fine. And if I run this code, I would assume that we will not get any complaints about that. And I am correct about this. There is no problems there, right? So once we have that, and we know what version we're in, having the quick reference card up is nice because the quick reference card will tell you everything you need to know about what exists in this version of OpenGL's shader language, which is not always easy to remember because even once you know what those are, you may not remember which ones go with which versions. Now this looks to me like the API language. So here we go. OpenGL shading language 150 quick reference card. Here we go. Although I gotta be honest, this doesn't look like the one I actually wanted. Okay, there's more of it. Yeah, here we go. I was like, I wanted more than that. So right here is where it starts. Okay. So the reason I think it's good to have one of these up, like I said, is it's hard to remember all the stuff that's in there even after you kind of are more familiar with it. So I like to have one of these so I can remember, oh, wait, is there a function that lets me sample a texture at a particular level of detail, at an integer position or whatever, blah, blah, blah. And you're like, oh, yeah, okay, it does or it doesn't have that. It's easy to kind of look through here and see whether that's in there rather than trying to learn it and remember it all. So that's kind of nice. But anyway, what you can see in terms of how this breaks down, you can see in here, this is the version directive stuff. And like I said, we're not going to use full 150 because I don't think we need it. So there might be some things in here we can't access, but most of the things we should be able to access just fine. You can see on here that a lot of the stuff is very self-explanatory, right? Like you can see all the types that exist in GLSL. They're all types that we have written ourselves, sort of. In Handmade Hero, which is like, vec2, vec3, vec4, all very familiar to you. You've got vectors of Booleans, vectors of integers, just like we did. Sometimes we would create, other things. You've got the matrices for 2x2, 3x3, 4x4, right? And you've got ones that are abnormally sized as well, like a 2x3 matrix. So all that stuff is very familiar. Some of the other stuff is probably not so familiar. You've got floating point sampler types. This is things that sample from textures. Integer sampler types also sample from textures. You got implicit conversions that will tell you how their conversions work. You can see here that they've got implicit conversions just like in C. You can create arrays, structures, and blocks just like you can in C. Blocks are special. They're not something that you've seen in C. Block is basically just a structure style thing that lets you know that something corresponds to a piece of code you're going to talk about in your main line. Because one of the things that you'll see us have to do as we get a little further down is figure out how to get data into these shaders from the outside, from our code. All the operators are the same pretty much as what you've expect and see with some subtle differences. So mostly you can use your intuition here. You've got assignments and bitwise operators, logical operators, shifting, multiplication, all that stuff. Most of the things you're used to having are there, parentheses, all that stuff is exactly as you expect. For vector components, it's exactly like C, where you do the bracketed initialized list. So the people who made these shading languages were C people. They made it look like C, and so most of the stuff that you expect to be there is there. You also have tons of built-in functions, so you get a math library that comes with this that's built in either to the card or to the shading compiler, one or the other. You don't necessarily know which at any given time, but they're guaranteed generally to be reasonably performant for whatever the operation is, what you could expect. So things like sine, cosine, tangent, taking the max to the minimum, doing a mod, a ceiling, a fract, a floor, rounding, all that sort of stuff. I guess floor they don't have in there. Yes, I guess you'd use frac. I don't see floor in here. Oh no, there it is. I was going to say it should be there. Floor, truncation, taking the sine, absolute value, powers, logs, blah 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 blah. So you've got a full math library in there as well. Linear interpolation is here. They call it mix. So also a smooth step function, which is like a little cubic curve, so to ease in and ease out of stuff. So there's a lot of things you can do here. Dot products, cross products, take the distance. All the things we implemented in our math library in Handmade Hero are here, and probably some that aren't. So they've got a lot of stuff to work with. And then you've got a bunch of built-in functions for doing things like getting information from textures, getting gradients, which are things that we'll talk about potentially if we ever get to them. We don't know if we will. noise values, that sort of thing. So there you go, right? And so understanding how to program the OpenGL shading language is pretty straightforward. You'll see once we get going. You have a lot of stuff at your disposal. It's all standardized, so you can just use everything that's here, and the compiler will make that into efficient GPU code, and you can just rely on it. Usually there aren't a lot of surprises there. Okay. So now, the way that this works is there is, for whatever reason, a main. They did actually call it main. So I don't think that's specified anywhere on here, so I guess you just kind of have to know it. At least I don't see it anywhere. Maybe it's defined. Maybe it's defined on here somewhere. I'm not entirely certain. But you start off in a main just like you do in a C program. And then one of the things that obviously is a little confusing is, well, okay, so I've got a main. This thing is supposed to operate on 16 pixels or 16 vertices at a time. How do I say what the result is? Like, how do I get information in, and how do I put information back? And the answer is it's all done by global variables. And so let me show you how that happens. All right. So let's say we're going to write some Vertex code, for example. What we have to do in the Vertex code, and I'll show you this in just a quick second here, but for starters, we have to have some kind of an input. So we're going to have some kind of an input vertices here. So like input vertices or input vertex, right? We're going to have some kind of input vertex that we have to operate on, and we're going to have to define that as something, right? We're going to have a main here, and we're going to have to define that function. But essentially what we're going to do is also have, after that, an output vertex, and we're going to have to write some code that does something along the lines of, output vertex equals input vertex. And obviously, probably, we're going to want something like our transform here. And so fundamentally speaking, a shader basically looks like this. It's going to define some global variable called an input vertex, and somehow, and we're going to get to that later, somehow that will get corresponded later on in our code with the vertices coming from our C code. So our actual code for Handmade Hero in the game will be setting some things so that the OpenGL subsystem knows what should go into input vertex. We're going to define something that's an output vertex here, and it won't actually probably be called output vertex because you'll see in a second it's got a special name. But we're going to basically assign that output vertex to whatever we do to our input vertices. And then we're going to have some information we're going to need, like this transform, that's going to have to, again, come from Handmade Hero, that's going to do the transform. And basically, this is what a shader is going to look like. The main is essentially, in your head, is going to be called for every input vertex. So every input vertex will go through whatever we write in here. And this can be as complicated as we want. This can be many lines. We can call functions. We can have loops. We can have ifs. But at some point, we have to assign something to the output vertex, and whatever ends up being assigned to the output vertex at the end is what will actually be output of the shader. Okay? And again, this, even though it's input vertex, output vertex, and transform, and it looks like it's only doing one thing, it's doing this for like 16 pixels at a time or more. Right? I'm sorry, 16 vertices at a time or more. Okay. So let's start with output vertex because that's the easiest. Instead of us defining a global variable for this, what actually happens is OpenGL has already defined a global variable for this. And I believe those are in here somewhere. Here you go. So you can see here built-in inputs, outputs, and constants. You can see here all of them are specified for what we care about. Here is the Vertex language. Here's what's coming in. We've got GL color, secondary color, normal, vertex, multi-text chord, and fog chord, right? That's, I believe, if you're using the fixed function pipeline, those will be coming in. Otherwise, you'll see there you can define your own, and which is probably what we'll do a little bit later on. But then in the outputs for this, you end up having a GL position somewhere. There it is. A GL position, which is going to be, no, that's not Fragment. Where is it? there should be an output to this somewhere. There it is. GL position. This GL position is the actual output in clip coordinates. That's going to be the thing that we're actually using, right? That the shader will actually output. So this is automatically defined by OpenGL, as are these other ones. Clip vertex, clip distance, and point size, we can output to if we want to override those things. We have no need to have any of those values be set to anything. We only care about the position because that's all we're using in the pipeline. So this output vertex is actually just this. And it's already defined for us as a vec4. So effectively, OpenGL had this defined for us at the top of the program, but we're not going to touch it because it's a special variable that it knows is the output from the shader. So then we have what our inputs and our transform are. And in this case, we have, I believe, GL underscore vertex if we use the fixed function pipeline. I've never tried to use the fixed function pipeline with shaders. Let's give it a shot. I don't know if it'll work or not. It probably won't. And we can go ahead and go to the primary way to do it, which is what we want to get to anyway, but we'll put it in there for now. So effectively, there's this being defined as well, which is the input vertex in this case. So we can do this. Oops. And so this is just saying the output is equal to the transform of the input vertex coordinates. So the XYZW here is going to get multiplied by transform, and it's going to be output to GL position. That is all we need if we had this transform. Now we know that this is a 4x4 matrix, right? And you can see in here, you got mat, and we could do mat 4, or we can type it in mat 4x4. Either one will work. I like mat 4x4. It's a little clearer, so maybe I'll leave it that way. But we know we want a mat 4x4 transform here, but what we don't know is where this would come from, right? Because remember, this is going to get called from our code, and our code, this is going to be executed on the GPU when we try to dispatch a batch of primitives, right? When we try to do some rendering, like a GL begin, GL end, that batch of vertices is going to have to go through this shader. Where does the transform come from, right? How is it going to get there? Because it needs to get passed, effectively, from our C code in Handmade Hero to the code operating on the GPU. And how is that going to happen? Well, the way that happens is there's this thing called a uniform, which when you declare something as a uniform, what that's trying to say is this is something that doesn't vary per vertex. That's where the term uniform comes from, right? It doesn't vary depending on the thing I'm operating on. It's going to be set by somebody, and then all of the vertices that come down in a set are going to use it. So what that means is we can set these uniforms before we execute a shader, and those uniforms will then be able to be communicated from our C code, right? So how that works is if you come up here and you can see render group entry, render entry bitmap, right? This is the code that we want to have happen. What we would do is in this code, we would have a call here, and we'll have to look up what that call is, right? It's GL uniform, but I want to show it to you and whatever. There'll be a call which will say, all right, I want you to bind, and it won't quite work this way because we'll have to look it up first. In fact, it's more like this sort of thing. What we will effectively have to do is take the transform that we want to be used here. And that transform, again, we actually do know what it is because we load it right here, right? We do this load matrix M4x4 proj transpose, this sort of thing. What we can do is just say, oh, OK, let's just keep this proj around, right? Every time we come through and we generate the 4x4 matrix, I can now specify that I want that matrix to be the matrix that gets used every time that you're going to do one of these things, right? So when we do this specification here, what we can do is say, We need to know what the ID is of this transform, and then we need to set that transform to be this value, right? And so what this will do is this will tell OpenGL, hey, this line will say, go look at the shader, figure out what your, what is the ID, basically what do you use to talk about the location where this string, this string's name goes, right? In other words, I should explain this. So we've got something that says uniform map 4x4 transform. And then blah, 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 blah shader, right? Here's my shader code. So, all right, I've got uniform map 4x4 transform. I've got some shader stuff here. And I need to be able to set this, right? So what's going to happen when OpenGL compiles this down, right? This is going to go through the compiler. Is it's going to go through a compiler specific to the GPU. So on this machine, it's AMD. So it's going to go through AMD's compiler, and it's going to output a bunch of AMD, right, machine code. So this is stuff that's going to be run on the AMD core, right? So all of our shader instructions are going to get compiled down just like they would have got compiled down if it was regular C code to x64. They're going to get compiled down to AMD machine code. That AMD machine code is going to be referencing a specific location in memory where it expects this transform to be. It's going to expect 16 floats, right, to be somewhere in memory. And it will have picked where that is. So it will have an address that it knows it's going to grab when it goes to execute this shader. This machine code will be looking at that address. Now that address is relative to the core because obviously it's working on a particular batch at that time. So it's not like it's necessarily a fixed address in the GPU's memory for all time, but it has some idea of, for a particular execution, there's some local memory for this execution, and where that is in here, it knows, right? So it's got, we'll call it an offset address where that's supposed to be. What we need to do is tell OpenGL, hey, we're going to give you that 16 floats. Okay, here they are. I need you to copy that down to the card, and I need it to go into the location where it needs to go for this shader execution, right? So what we're doing here is we're saying, hey, go look at when you compiled this shader. Tell me where this variable ended up, right? Give me back a cookie, basically, that I can use to talk to you about that location, because I don't need to know what it is, right? I just need to tell you to put something there, and here's me telling you this is what I want to put there, and then it will go down there, right? And then for this execution of the shader, for the GL begin, GL end pair here, it will take that and use it, right? It'll use that as the value of that variable. So that's effectively what we need to do. Obviously, we don't need to do this every time, the lookup for the name. And that could be expensive for all we know. So what we really want to do is have in here something like this, right? Where our OpenGL that we're using, we can just say that it's a global because it's never going to change. So when we do our initialization, and we do create program, we're going to want to do that call down here, right? So that it's snapped and saved. Okay? So that's how the Vertex shader code will work, and we need to work out what those calls are, obviously. But other than that, we are now OK to move forward. So we have our GL position. We're doing our transform there. And we've got our fragment code now that we need to create as well. Same exact thing applies here. We're going to have to define a main, and we're going to have to do something with what's going on, in terms of our inputs and outputs. Now, what you'll see here for the first time is we now have a way that this needs to get communicated things have to be communicated from the vertex shader to the fragment shader, which we haven't had to do yet. Because remember, this GL position is a special variable that outputs the position. The reason there's a special variable that outputs the position is because it has to go into this piece that we don't control. Oops. Remember I said there's this rasterizer in between, so we do some stuff with the vertex shader. There's a rasterizer that rasterizes the triangles. Then we get the fragment shader. This guy needs to know the positions, because it needs to know the corners of those vertices in order to rasterize the triangle. So GL position is defined as that communication, right? GL position is the value you need to give the rasterizer for those vertices. So we didn't have to define that because it's already something that's built in, because the rasterizer has to know it, so it has to be known to the GLSL. It has to be something that GLSL understands natively. It can't be a variable we define. However, we now get to something where in our fragment code, we actually do need to know something, because we have to know what texture we are going to be sampling from and where, right? So we're going to have a texture coordinate that gets passed down here, right? We're going to have some way of getting texture coordinates in, and some way of outputting texture coordinates to the fragment shader. Now that I think about it, though, we can probably hold off on that for a second. So hold that thought, actually, because we should probably get this working without textures first. All right, so in the fragment code, the same thing is true as in the vertex shader code. If you take a look at these vertex language built-in outputs and constants, right, you can see what all of them were there. And then we've got the same is true for the fragment language. So you can see all the in values, right? You've got the fragment coordinate, whether it was front-facing, the clip distance, the point coordinates, which are if you were doing the point sprite stuff, that's the same as the point size thing here. It's, again, not something we care about. What the primitive ID was, again, not something we care about, and the fragment depth. So you can see here we've got some inputs, none of which we really care about, and we have an output which we sort of care about potentially, right? This is the depth value, which we might care about, but you'll notice the color actually isn't there. And the reason that the color isn't there, if I remember correctly, is that actually, for reasons I do not completely understand, and really couldn't say what the reason was, instead of there being a predefined output for that, you can actually just define your own, if I remember correctly. Now, I thought that you could also use glfrag color. And I feel like that might be something that comes in a later shader language version, meaning when they went up. In fact, let me just look to see if I'm right about this, because I'm just curious now. Yeah, OK. So let's see. Nope, it's still not there. So I guess maybe I'm just hallucinating about that. But anyway, what I was going to say beforehand, before I kind of got sidetracked on wondering whether or not that was true, is my recollection is that just whatever you define as an output variable ends up being, if the first one is the output color. And if you define more, then there are more output colors that go to more buffers or something weird like this. All right, so let's look at that for a second. So as you can see here in the pre-declared variable declarations, you can see there's these ins and these outs. Those are not in C, right? We never use in and out declarations in C because global variables are just global variables. In shaders, since they're these pieces of code that kind of get welded together with known things on either side, like the fragment shader has inputs from the vertex shader and outputs pixel values. The vertex shader has inputs from the tessellation of geometry shaders or the OpenGL pipeline itself, and then has outputs that go to the fragment shader. There's this notion of in and out globals because they're the things, the context in which the shader was being executed, what comes in, what goes out. We can use those to say, OK, there's an out variable here. It's going to be a vec4, and it's going to be the fragment color. And then all we would do is say, well, OK, whatever that is, let's say the result color is a vec4 that's just red. Right? It's just red. OK? And so again, this would, in theory, be a completely usable pipeline if this transform value were set. It would work, right? It would be something that takes in vertex coordinates, transforms them out to positions. The positions get rasterized in between these two. Then it calls the fragment code for each pixel or sample that got rasterized. It has to produce an output color. So at least one output vec4 has to be declared for the result color. The result color is going to always be set to red, but in the future we'll set it to something more complicated. And that's the end of it. Now we have to go up here and actually put in this, this code that I was talking about before. And since we have a quick reference card up, we might as well use it. We actually have in here all of the stuff that you can use for shaders. You can see the uniform calls being talked about here. This is all we really need. You can see it here. We've got uniform matrix FV. There's the int location, the size I count, the Boolean transpose, and the const float value. That is exactly what we want, right? We're trying to specify a uniform matrix. And again, we want it to be a 4x4 matrix, which they don't support. Oh, I guess they don't support a 4x4, so you just put 4 at the end of it. All right, so whatever. So that's effectively this, but they don't have it. So I was going to be like, that would be bizarre. I've done this many times, and I don't remember that. I guess it's just they didn't bother giving the 4x4. This is only for odd sizes, for non-square sizes. So there's that location, like I said, that we have to query. We then have a count. We only want to specify one matrix. It allows you to specify a bunch of matrices in bulk. There's the transpose. Now, one of the nice things about that is the transpose part, like I said before, we can now, we were doing that transpose manually ourselves. And remember when we did that, I said, when we get to shaders, we won't have to do that anymore. Well, that is 100% the case now. We can, if we want to, just stop doing this entirely, and instead say that proj just equals clip proj, and it will work. So that's pretty cool. But for now, since I want to see if I can maintain these two pipes just for a second as we transition them over, this may be a complete disaster to try and do, but we'll try it anyway. We're just going to say, OK, for now, we won't transpose, though. So again, location, count, transpose, and value. And so and there's that value, which is just the floats of that matrix, right? So that's what we need to do there. And of course, I actually have to, well, you know what? That's fine. So we're going to have to load that variable, certainly. But then while we're at it, we might as well grab the other one we need too, which is that when we're doing this transform ID stuff, we've got to have a way of getting it. And what you can see is we want to get this location ID. We need a place to get that from. And you can see here with uniform values, you've got this get uniform location, right? And that's exactly what we want to be able to do. We want to be able to get uniform location for a program and a name, right? So that's the function that we need. And so this OpenGL basic z-bias program that we get back, that's actually what we want to get our transform back, right? So we need get uniform location, and we need the ability to load the uniform. But in addition to that, what you'll notice here is at no point have we ever specified how to actually say that we're trying to run that program, right? So at no time have we actually told OpenGL that we want this program to be run. So we need some way of specifying that, right? And we can do that by using the called GLUseProgram. So what GLUseProgram does is it says, I'm going to tell you the program now that I want you to actually operate on. And so that program is that one that we compiled, right? It's the basic z-bias program. And again, I've never tried to use the fixed function pipeline like this before, and I'm pretty nervous that it's not going to work. So we might have to first port everything over to the program version before we can get it working. That's not a lot of work, so it's not a big deal, but just fair warning, that may happen. So be advised. All right. So that's all we need at the moment. So we just have to get those two, uniform matrix and get uniform location. We just need those two. Functions, and then we should be good to go. So let's see. Let's just go ahead and grab that, get uniform location. And then we also want basically all of this stuff. We might want any number of these, but probably none of these. We're probably always going to load in bulk. So I would say we probably only really need, this one and this one. We probably won't use much more than that. Oops. Okay. So these are the new functions we will need. Again, there's nothing mysterious here about these, so I'm just going to go ahead and do exactly what we always do with them. I don't know how I did those before. I guess I did it that way. And then these get lowercaseified. So there you go. And so now I just have to actually get these. Like so. And last but not least, paste in the name. I suppose there we go. So now we're effectively doing everything that probably would be necessary to bind things together here. But again, we may have to kind of push a little bit further before we can actually get things running. I'm going to go ahead and run first and see what's going on with our shaders here, because we may have errors and stuff. Oh yeah, that's a good point. We never actually put in the main. I just left that in there. So the GLSL declaration for main, I don't even remember what it looks like. So that's a good question. So it looks like it's just void main void. Which is fine. Although it seems to be complaining about our vertex shaders having one, which is odd. Oh, no. I only put that in the fragment shader. There we go. So you know what? I guess now that I think about it, is that even when I did that compile status there, I may have done that slightly wrong when I put that in there. Compile status. Let's take a look. Because compile status may not be something that's defined in the program IV. Let me go ahead and just grab out. Because we're now compiling properly, but we're getting an error, and I'm probably just asking that for the wrong thing. So let's double check here. Docs.dl. Let's take a look. Yeah, so you can see compile status is not actually on here. So compile status must be only for get shader. So I should be able to just say get link status is probably all I really need, would be my guess. Because the link status would fail, presumably, if the like presumably I can just do this. All right. So hey, I guess that actually worked. Which I wasn't expecting it to, because like I said, I wasn't expecting it to actually be able to mix with the fixed function place spline so smoothly. I mean, I know it's supposed to, but you know, that's not a path that anyone cares about in OpenGL because nobody uses it, right? But hey, there you go. So there's that red that our shader is doing, right? And remember, this stretch to infinity is because our W coordinate is set completely nuts. So hey, let's see if our shader really is working. Let's go ahead and take that W coordinate and correct it, right? Let's go ahead and say that GL vertex, I'm going to define a vec4 here, which is input vertex equals GL vertex, right? And then let's take our input vertex and let's set the W coordinate equal to 1, right? So that now we're not having that, because remember, we were using the W, we modified the pipeline to specify in the W coordinate our Z bias value, which ruined the W coordinate, which is what caused everything to stretch into infinity when we did it. Now in our vertex shader, let's take that out. And hey, look. Now we're all correct. So now you can actually see our vertex shader is running, and it's actually doing something useful now. It's not particularly great because we're just drawing red rectangles, but it's pretty close to working, right? I mean, that's roughly what we wanted. So that's great. And now all we have to do is say, all right, let's start taking this a little bit further. So first of all, what we could do is say, well, you can kind of see here where we create our GL position. This GL position is going to have the X, Y, and Z W on it, right? So what'd be pretty interesting to do here is say, well, OK, what if we just use that Z bias value that we have? Our GL vertex.w is the Z bias value that we have. We could, if we wanted to, offset the Z that we use for Z buffering by that value, right? Now that value has to be set to something reasonable, obviously. because if we don't set it to something reasonable, it has to be reasonable based on what we're actually doing to our values here, right? So after the transform and things are mapped into the z space, that z space is -1 to 1. That bias value has to in some way correspond to this, right? But if we want to be kind of lazy, which I kind of do right now because I don't want to go work out any math that I don't have to yet, you can imagine saying, well, we have a z bias value. Let's just transform 2 points. And then we'll set the z value to be whatever the biased one's z value is. And that's how we'll do it, right? So we can say vec4 z transform. And what that'll be is times the input vertex. Well, let's do z vertex. What we'll do is we'll just take the input vertex and we'll take the z coordinate of it, right? And we'll add to that z coordinate whatever the z bias value was, which is coming through in the w coordinate, right? We'll transform it, and then after we get the z transformed version, we'll take our GL position, the output that we're going to have there, and we'll just overwrite, we'll just overwrite the GL position's z coordinate with the z transform's z coordinate. Right? So now what you can actually see is we are getting the biasing that we wanted. We're no longer clipping through the cubes, right? Now we haven't set up texturing yet, so we're kind of just sitting there looking pretty dumb, but because we're just all red values. But you will notice that these things, these sprites, are still clipping straight through the cubes. We just never see it because their z bias is always taking care of it. So did you see how I did that? All I did was I just wrote in the shader code. I was like, all right, I have an input vertex that's coming in. I know that the w coordinate is secretly the z bias, right? So I'm going to overwrite the z value that I'm going to actually use. I'm going to overwrite that with 1 because that's what I actually want to use for my transform, right? Then I'm going to create another vertex, which is the same as the input vertex, but instead of having its normal z value, I'm going to offset its z value by that z bias, right? And you could think of it this way. Right? Another way to think of it might be, I think you can do this. We're going to find out. So another way to think it might be, okay, the input vertex is actually whatever the GL vertex is, x, y, z, but then its w coordinate is going to be 1, right? Then the z bias is actually coming out of the w coordinate of the input vertex, right? So we're using the x, y, z and the w for 2 separate purposes. Then we're going to create this synthetic vertex that's the same as our input vertex, but with the z coordinate offset by whatever this bias is, right? Then we're going to transform them both. And in fact, I can make this clearer by going transform the input vertex, transform the output vertex, right? I'm sorry, transform the input vertex, transform the one with the biased, right? Then when we want to do our output, the output is just going to be and off you go. So hopefully that's a little clearer now, right? So we take the inputs, we bias, we create a secondary point that's biased, right? That's up further. We transform them both, and then we just use the z of the transformed one. So it's as if it had been raised up in terms of its depth values, but in terms of where it actually shows up on the screen, it uses the same thing. Right? Now, this may look really inefficient, right? But actually, it's a lot less inefficient than you might think. The way that these shader compilers work is they basically do, single static assignment kind of style form, where they basically take a look at the thread that produces an output. So it knows that the only thing it needs is GL position. So it knows that the only values it needs are these 4. So it knows that the only thing it's going to use out of Zmax transform is this. So it knows that it doesn't actually have to do this entire transform. It can just do the Z part of the transform, and it won't ever bother doing the rest. So it does have an optimizer that is going to do relatively reasonable stuff in terms of only computing the things it needs. That is true. Now, it's not an amazing optimizer, so don't get too excited, but it's definitely going to be able to do some basic stuff for you. So you don't have to worry too much about that kind of code structure. It's not going to be literally executing the stuff that you wrote in. All right. So in order to get ourselves back up to actually working here, we need to put our textures back in, because right now we don't have any way of sampling from textures, and we need to sample from textures. So inside our fragment code here, we need to be able to get a texture coordinate. And so this is where we need to start having the idea of colors and textures getting passed through. So what happens here is we've got, remember, uniform. And like I said, uniform is something that gets specified once for a whole batch and then just gets used. So it's coming from the C code. That distinguishes itself for something that's per vertex, like this GL position output or this GL vertex input, which are per vertex. In order to get texture coordinates in, we want another thing that's per vertex. So what you typically use, they use a thing called varying, for example, to distinguish it from uniform. I don't know what this version of the shaders actually uses, so let's double check real quick, because it changed actually. I remember it changing. It used to be varying, or it used to not be varying, and then it was, or I don't even remember. It was all big fun stuff. Anyway, you can see here we got qualifiers, storage clause, in, centroid in, out, uniform. So it looks like there's no need to specify varying. So if we simply don't say uniform, it is assumed to be per vertex, is how this version of the shader goes, as far as I can tell. So let's go ahead and make that happen. So we know we have an in value here. We know it's going to be a vec2, and it's going to be the UV coordinates, right? And we'll call this input UV. And then we also know that we want a vec4 for color. Maybe I won't type input, I'll just type in. Right? So now if you look at that, you're like, well, OK, I've specified things that come in. They must come from somewhere. I don't know where they come from. And it's like, OK, we don't really know where those come from. But then in terms of output, we have to do the same thing. Because remember, the place we actually want this eventually is in the fragment code. So in here, we want the same thing. Maybe we'll call this frag UV and frag color, right? Or maybe vert UV and vert color. I don't know what we want to call this. Interpolated color. This is basically when we get down to the fragment shader. Each vertex had a UV coordinate and a color, and we're interpolating that along the line. Inside the triangle barycentrically. I don't know what we want to call this, but this is I mean, I guess frag is probably the easiest thing for now. So here we're going to need this and this, and we need to declare these in the fragment shader. In addition, we need one more piece of information, usually. And you can see it here, which is smooth, flat, or non-perspective. Now, what's interesting about this is something that you can't really appreciate in Handmade Hero because it doesn't really come up super much in what we were doing, but it's important to understand, so I'll kind of go over it just really briefly here. Was it no perspective. All right. So 3 choices for variables that are in the fragment shader, and why do we need these? Well, okay. Inside a vertex shader, remember, we've just got vertices, right? X, Y, Z, W. These are basically coming directly from the app. So I'm specifying these in C, and the vertex shader is just munching on them and outputting stuff for the rasterizer, right? So it's outputting these X, Ys, and depth values, right, for the rasterizer. At no time, there wasn't anything here that needed to interpolate any values that it got. But once these come to the rasterizer, right, it's going to line up these as a triangle. It's going to go like, oh, here's this guy, and here's this guy, right? Here's my triangle. Well, I now need to shade some stuff that's in here. How do I know what to pass for these values if all of a sudden I start augmenting this with like U and V, right? How do I know what the UV is in here? Because I know what the UV is out here. I don't know what it is in here. And the answer is it has to do a barycentric interpolation, just like we did. Remember, go back to the software rasterizer if you aren't comfortable with these things, because we did them all. We need to figure out what the UV is using some kind of a barycentric interpolation between these 3 points. But there's multiple ways you could do it. One way is called flat in OpenGL. That's if it's always just stays the same, right? So that would mean that whatever like the first vertex's ones are, the whole triangle gets it. So there's no interpolation at all. It just doesn't interpolate. The next kind is called no perspective. That's what we did in the software rasterizer. That just says, I don't need to do anything fancy. Just go ahead and use whatever the barycentric interpolation would give you at this point in screen space. Smooth, on the other hand, is for normal 3D games, which we are not really, but if we were, and this would actually be the case with our cubes when we do our cubes, because they do have things that slice downward in Z. What that says is, hey, let's say we were looking at something head on, like the wall of a dungeon or something, right? This doesn't interpolate evenly across its surface because it's going backwards in Z. So things that are close together back here are actually much further apart than things that are close together up here, right? Just perspective. Things that are closer together get bigger. So when we interpolate the texture coordinates, we want to interpolate them with respect to perspective. So a motion up here should be moved, this should move the UV coordinates more than motion back here should, right? If that makes sense. That's the bad way to say it. But point being, what we're trying to do is simulate the fact that we actually did a perspective transform on the texture rather than just warped it, right? And this is like if you remember looking at the PS1 graphics, I think we mentioned this before, like PlayStation 1 was all kind of warpy. That is exactly what happens when you don't do perspective correct, or Ultima Underworld's walls, right? That sort of stuff. So smooth is what you would pretty much always do by default unless you really wanted something specific, because that's the one that does correct 3D interpolation. You only would specify the other ones if you had some special reason that you wanted them. So you'd know if you wanted them. If you aren't thinking about it, you want smooth pretty much. So let's suppose we get these in here, right? Oops, that's supposed to be Vec4, right? So let's suppose we get these in here. Then we would be able to do some things like, say, if we want to do modulation, right? There's a modulate. We can just multiply. Now, they don't use Hadamard product in their stuff. They just do multiplication is a Hadamard. So times is the Hadamard product. Then they use dot and cross, the words dot and cross, to specify dot product and cross product. So those are the three vector multiplications they support. So we can do modulation by the fragment color, just like we do in the software rasterizer, or just like OpenGL was doing before. And then we can also do this frag UV. We can look up a texture, right? So instead of this red, right, like here's our vec4 of red. So instead of doing the texture sample as just pretending we have pure red as a texture, we can go in here and say, OK, let's take this UV and let's get a texture sample. So how do we get a texture sample? Well, like I said, there's a whole bunch of things built in for doing that. Where are you? There you go. Texture. Grad offset. Here we go. Texture lookup. So here's texture. You can see that there's all these different things, sampler, 1, 2, 2D array, blah, blah, blah. What we want is just the basic. These are for things like cube map sampling or texture array sampling, whatever. What we want is we want something that's a glvec4 that's going to give us back a full sample. We want a 2D sampler, right? So we probably want something that looks like this, where we pass in a UV here and the sampler that we're sampling from, and it gives us back the color. So that's the one that we want. So we want texture. We need a texture sampler. And then we need just that UV, which is right there. Okay. So the only other thing we need now is a way to get this texture sampler. And again, this is like a thing that is much like this mat 4x4 up here. This is something that's uniform. It's set one time, right, by the batch. And this is the texture that we're going to use. And it's got to be set from the C code. So it's something that we have to tell the GPU to communicate down to us, right? Same exact thing as the transform was up here. So we need to say that we have a sampler too, because it's a 2D texture, right? And that's all we need to say. That it's a floating point texture sampler, uniform sampler 2, texture sampler. Then it will go ahead and say, all right, assuming that someone bound something to this at some point, and we'll have to get to that later, then we can make that happen. All right. So what should happen now, and let's just go ahead and I'll show you the error first, and then we'll show you the solution to it. So we should get compiler error, we do. And the compiler error should be that we don't actually have the inputs that we wanted, right? Oh, well, actually, I've got a different one too here. Internal error, unexpected qualifier, texture sampler parse error. Did I specify something wrong? Oh. It's not a sampler 2, it's sampler 2D, right? Yeah. There we go. Oops. Well, that wasn't what I was expecting to have happen. So I was expecting an error there, and I'll tell you what the error was I was expecting, but I guess it's not an error for whatever reason. So you notice we've got these inputs here, and these inputs, I guess it just defaults them to 0. These inputs aren't specified, right? Was the point that I was trying to get to. And so what we need is a way for our Vertex code to output what these values should be per vertex so that they can get interpolated by the rasterizer. So what we need to do here is we just need to specify these as output variables that line up with what we expect to come in. So our output names here just have to line up with our input names here, and then when these two programs are linked together, they will line them. They will the shader compiler will understand that it's supposed to output stuff from stuff that gets written to here gets read from in here, right? That it just needs to be able to make that sort of that binding, right? So what we want to do is we just want to pass these through. We want to output a frag UV that's whatever the UV that was inputted, and we want to output a frag color that's whatever was inputted. So basically, we're assuming these come from the vertex stream somehow here, and we'll talk about how to get that in a second, and then we're outputting them like this. Now, I think, again, fixed function pipeline-wise, we may be able to cheat here and not quite start doing the array specification stuff that we would need to do to define our own vertex streams yet. Because I believe, yeah, we've got GL multi-text chord and GL color. So we can actually just forego these for the moment and actually just say GL multi-text chord 0 and GL color. Those are the fixed function versions. And so in theory, those can get bound and output to the fragment shader. Right? Oops. Under a GL multi-text chord, did I? Did I spell that wrong, or is that not supported in this version? Multi-text chord 0. Because that is the value, is it not? GL multi-text chord. Vertex shader was fine. Fragment shader was fine. Frag color interpolate modes do not match in 2 stages. Ah, yes. Sorry. The smooth needs to be replicated in both places. I don't know why, but it does. All right. So we need some way of getting the texture sampler and the texture coordinates set up here. I don't know why I can't access multi-text chord. It may be because that isn't actually in this version of the shader language. Let me take a quick look to see what the deal is with that. Again, I'm trying to do something here that, just as the transition, that we really are on kind of off the beat. We're off the beaten path, which is using the fixed function pipeline with shaders. Normally, you just use one or the other. You don't mix and match like I am. So I'm pushing it a little bit here, but we got this far. I might as well do it because, like I said, it's been nice being able to show you the individual steps, not having to do the whole thing in one big kerplunk. So yeah. So let's take a look and see what the deal is there shader-wise. Let's see. GL multi-text chord. I just want to know what the shader version is for that. Is there maybe in this shader version there was just a GL text chord? Was that a thing? So maybe this just isn't allowed anymore? I don't know. I'm confused as to why. I'm going to also just try this because I'm just curious. No, okay, so that looks like that was correct. So it looks like it's just a version mismatch. So GL text chord is the thing. And so we only want the first 2 values of it because we're only outputting 2. We're not, and texture coordinates are actually defined as full 4-dimensional coordinates on input. So we can just use just the U and the V part, which is all we wanted. And then we should be good to go, potentially, I guess. Cannot apply dot operator to an array. Oh, so it was actually just named differently, but it is still GL text chord. It is still a multi-text chord array, I guess. All right. Fair enough. All right, so I believe we are now passing down everything that we need to pass down. The only problem is we don't actually have a texture sampler set up, so we don't actually have a way of accessing the texture, right? We just named this phantom texture sampler, and we're like, hey, there should be a texture sampler. I don't know if we can access the fixed function pipeline there, but I guess I'll try again just to continue with just doing it one step at a time there. Let me take a look at the quick reference guide and see if that is actually true. Fragment language, it doesn't look like it, right? So it doesn't look like those are defaulted to, those samplers are defaulted in any way. It looks like you have to specify a texture sampler, unless I'm very much mistaken about that. Yeah, it looks like it. All right. So the last thing we have to do then is just to get this texture sampler bound as well, right? So again, this is exactly analogous to the transform thing. This is something that per batch we want to set a texture sample. So we want to set a texture for the sampler. just like we set a transform for the vertex shader. So what we need to do in our OpenGL calls are we have to actually have a thing here, which is the texture sampler ID, and that's going to get out of that program the texture sampler, right? Now that'll work just fine. The only problem is we don't do anything with it, so we're going to have oops. So we're going to have to actually do something with it at some point. So what we need is, when we're doing our GL uniform matrix up here, we bind it. We kind of need another GL uniform here, which is going to specify that we want our texture sampler to line up with some kind of a texture that we have bound to something, right? So we essentially need to do a GL uniform. And in this case, I think I misspoke before, actually, now that I think about it. I guess we do need a GL uniform I in this case because we need to set the texture sampler up, and we're going to have to specify an integer, right? So basically what we're going to do is we're going to set the uniform. We're going to set it to be which texture slot it's in. Oops, sorry. OpenGL. Yeah. And it also occurs to me that this should probably have this going on here, right? I'm pretty sure you have to bind the program to set these uniforms. I don't know why that worked before, but I guess it did. Anyway, we're going to have to specify a uniform here, and the uniform is going to have to bind the sampler ID to something, right? Now this part's a little confusing. Again, all of this binding stuff is really, it's a really messy part of the API. It's not done particularly well. It never really gets done particularly well unless you scale all the way up to NVIDIA's bindless extensions are the only time that I've ever seen it done properly in any API, really, for this sort of stuff. So there's that. But what we need to do here is we need to basically say, for this uniform location, we need to sort of correspond it to something texture related in OpenGL. And the way they chose to do that was basically with the concept sort of texture units, in the sense that, like, OK, we're going to treat the texture sampler as if it's basically just an index. So we're going to specify what index of the texture unit we're going to, which texture unit index we want it to use. So we'll say, OK, bind the texture sampler bind the texture sampler for this ID, bind it to unit 0, or bind it to unit 1, or bind it to unit 2. And then we still talk to it exactly the way we talk to this stuff, right? That's how this actually works. So yeah, we don't have time to probably get this working, but let me just go ahead and grab that function. I can at least do that much. But I thought that bind program was necessary to use those uniforms, but we didn't do that. I don't know why we didn't do that. Hold on a second. Let me just take a look. Modifies the value of uniform variable, referring to blah, 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 blah. None of this is what I want. The commands, my single uniform value, yeah, blah, blah, blah. Yeah, so GL uniform I and GL uniform IV are the only two functions that use uniform variables defined as sampler types. The only sampler type function, right? But I don't know where it says whether the program has to be bound. Well, doesn't matter. Anyway, point being, let's just finish up what we were doing. We can take a look at that again. So let's go ahead and do GL uniform IV. Should be here somewhere. No. there it is. So in this case, we just want GL uniform 1I. And same thing here. So bind program, let's see here, texturer, like that. So bind program, I guess we should also grab, because I'm pretty sure you need it. I guess I just couldn't find any positive confirmation that we actually did. But I felt like that should probably be there. Is it just use program? So is it just the use program sets it in and of itself? I don't have to bind it? I guess not. Oh, I guess not. All right. Okay, cool. So I don't need that. Good. Okay. So I think that's about it for this week. We'll have to wait to do the rest of the texture stuff until next week, but we're almost there. So we're close. Close but no cigar. We will have to, yeah, like I said, play around with this a little bit more. I'll leave this in the OpenGL code. I'll leave the texture sampler just so we can see things. I'll leave the alpha value at 1 just for fun, so that we can actually see where things are. But other than that, we'll go ahead and go to the Q&A, and we'll do the texturing next week when we can both do the texturing and make sure that we're handling alpha correctly and stuff like that in there, because we'll want to put in an alpha discard and stuff like this. So we have a couple more things that we're going to want to do, but we're pretty close. How is there, wait, seriously? How is that possible? Because I don't have any hotkeys set. None. Control W. Are you nuts? How did that get set? That has never been set before. That must have got set for some other reason. Well, that's terrible. Yeah, I guess I don't hit control very often is probably why we never noticed it before. That must have gotten set during some stream we did for some other reason. I'm glad we now know what that is, because that would have plagued us for a while. All right, let's verify that that won't happen again. Control W. Let's see, did that do anything? No. Good. No, it's still doing it. I have cleared the hotkey, but it's still doing it. How do I make it stop? OBS seems to really want that hotkey. So those hotkeys are still there, even though I've cleared them out. I'm not sure how to make it not do that. Well, I can try like restarting OBS. Check your global settings. Keys. Yeah, I don't think there are any. Well, yeah, that's really problematic. I mean, I'm definitely going to have that accidentally happen again if I can't get rid of that, because that's real bad. Thank you, OBS, for that wonderful feature. Well, can I set it to something like Control-Alt-Shift semicolon? Nope. Boy, this hotkey sure is interesting. Yeah, that's a good idea. If I just deleted these, it wouldn't be able to switch. Let's do that. Remove. Remove. All right. That's what we want. Let's just leave it like that so it's less risky. Rooktag, now that we've gone OpenGL, do you still think the Raspberry Pi option is still on the list? Actually, the only way we were ever going to do a Raspberry Pi is if we did OpenGL, because, or some 3D hardware something, because unfortunately, the Raspberry Pi is, a lot of the power on the Raspberry Pi is in the graphics GPU. So if we ever do a Raspberry Pi version, we're going to have to do it with the GPU. It doesn't have enough CPU performance to run a game, I don't think. Software rendered. Would you show us the code for what you have done in the last 2 to 4 minutes? Yes. Let's go ahead and just go over what I ended up doing, just so it's clear. Let me make sure this OpenGL, this thing is kind of okay. So that seems to work okay. All right. So all I did was I said, well, okay, we're going to need to do the same thing with the texture sampler that we did with the transform. So it's a uniform value. It's going to be this thing called a sampler, and what a sampler is just a way of getting texture samplers, right? Texture samples. We don't know anything about it, meaning the graphics card doesn't tell us how it's doing that. We just know that at some point we can call texture and give it a UV coordinate and one of these samplers, and it will go get us the corresponding sample from the texture, and that sample will do whatever the thing is set up to do in the OpenGL texture unit. So if it's set up to do bilinear interpolation, it'll do bilinear interpolation. If it's not set up to do bilinear interpolation, it won't. There's also ways of trying to tell it inside the shader what you want to do, whether you want to do bilinear, whether you want to do this or that, right? So it's going to do that sample. It's going to get us back the texture sample. Then we're going to use the texture sample to do whatever texturing we want to do. That all is just very straightforward. However, this thing, at some point, just like the transform, has to get passed down, right? So we need some way of the C code being able to tell the shader code, this is what you're supposed to use for texture sampling, right? Which texture unit you're supposed to use. So what we had to do that was to add, well, first of all, we had to add texture sampler ID, which is the same as the transform, just getting the location out. So it's basically tell us what uniform location we're supposed to use, right, to talk about this value. So we did that. And then the other thing that we have to do is when we actually go to call that, we have to, where is it? Where we do use program. Here you go. Where we do use program, we then have to say, OK, just like we set up the matrix, we have to tell you what texture sampler we're using. At the moment, we haven't done anything to get that working. So like I said, that's not really going to do anything. I just am setting it to 0 at the moment. So you can see that it's just this, nothing particularly, it's not actually working yet. But that's all I did. That was it. It was just to get a way of now specifying some piece of information that goes with that texture sampler. Oh, OK. So we got a little help here from WGG25 on the GL text core thing, because this was the part that I wasn't sure about before. Like I said, I'm not sure where that's coming from. He was saying that it's actually specified like that, and the GL text core one is an output one for fixed function pipeline. So if that's the case, then that would be nice, because I was just trying to figure out how to get the fixed function input, which, again, like I said, normally you don't do. But let's see if that works. Oh, hey, there we go. So that was the only problem, was that we weren't getting the right fixed function input there. Thank you very much. In this case, I can remove the setting it to 1.0 there. There we go. So now we're getting what we expect to get pretty much in all cases. Actually, now we're basically restored to what we want. You can see this is what we're actually outputting, these sort of flattened sprites, right? But it looks correct now when we look at them, right? You can see the trees look like what they should look like and everything. But we still do have one problem, one that we probably can't fix on this particular card. As far as I know, because we don't have, well, I mean, we could fix it, I guess, by trying to work around it in the shader. But we don't actually do, we don't actually have the GL sRGB flag set still. I don't know if you remember, but when we create our multi-sample buffers here, for whatever reason, even though it's supposed to, this card is not allowing us to set the internal texture format to sRGB, which is very bizarre, right? So I'm not sure. Yeah, we don't have a lot we can do to work around that, although we could do it directly in the shaders ourselves, but seems like a bad idea because we want to use the hardware for it directly. Yeah. Miblo, I don't generally. I have to go to both Q&As and type in pound Q&A, so it doesn't automatically replicate anymore. I think the Handmade bot used to do it, but it doesn't, or InsoBot used to do it, but it doesn't anymore. Sometimes I forget to put it in both. Tag, you mentioned the new assets will not be rectangular like the current assets. Do we need to update the asset pipeline? No, the new assets are rectangular. Abarishu, are we completely dropping support for the software renderer now? No. We will definitely make the software renderer work as well. I don't know when we'll do that. We might choose to do that much later on because we don't need it for anything, but I would like to have them both running eventually. Vertex says, I mean the hero head versus body versus cape are all the same shape. Oh, yeah. Yes. We will have to do some changes to the code when we update the artwork, certainly. But that'll be true in a lot of ways. Can you explain with a little bit more detail how the Z-bias thing works? I'm not sure I understand it. Yes, I can. So our situation as we had it was that we've got the camera looking down at a very steep angle, right? And so we've got sprite cards that are necessarily parallel to it so that they can appear, like sprite cards on the screen. But of course, if they are laying down that flat, they get intersected here by other geometry that they really should be in front of. We want them to look more like they're standing up straight like that, but that would make them warp with the perspective projection. So we want to leave them so that they're face onto the camera. So we have two choices here. One is that we could actually have them stand up straight and then adjust the, if you took, this is looking at it from the side. If we looked at it sort of more head on, right? Here's those two cubes. And we've got the sprite card that looks like this, flat. One is to say, well, okay, we're going to go ahead and widen or shrink part of this. So we'll go ahead and, move this up to here, but we'll shrink it like that so that the perspective that, projection that fans it out will make it still appear to be a rectangle, right? Because as it gets closer to the camera, it's going to get, bigger. So if we don't have it in exactly in one, I should back up and say, anything in an XY plane relative to the camera where the Z values don't change, that's going to be a perfect rectangle on the screen with all four corners right angled, right? But anytime we make it come out of that plane, it's going to change the apparent size of the top or the bottom, right? It's going to shrink or expand. And you're going to end up with something that on the screen looks like that or like this, right? So one way to do it is to make the opposite parallelogram in 3D that will undo that projection so it still projects to a rectangle even though it's not. The other way to do it is to leave it in the plane, and because the only thing, remember, that determines who shows up is the z buffer, is to just pass the z buffer values from this, but pass the actual coordinates from this, right? And so that's all we're doing. What I do is I say, okay, every vertex now has an x, y, z bias, right? So the w coordinate is actually z bias. In the shader, I force that value to 1.0 so that the transform still happens as if it's x, y, z, 1, right? So that just works. But then what I do is I take what this value was and I transform a second point that's x, y, z plus z bias, right? That gives me what the z coordinate would be at this point. And then I just say that that is the new point, x, y, and whatever that transform ends up being, right? So you can see that happening in the code here. The input vertex comes in, I take just the x, y, z, and I slam this w coordinate to 1. So then I know that I'm going to transform it just like it normally would be if we didn't have the z bias at all, right? Then that transform happens right here, right? Z-min transform is transform in vertex. I use that for the x, y, and w values. So the only thing I want to do now is change the z value, because remember the z value is only going to get used for z buffering, right? The w value is what will do the divide, and we're using the w value from the original vertex, so it's unchanged. So it will project to the right place in screen space. But to compute the z coordinate, what I do instead is I say, all right, let's make a new vertex that's the same as the input vertex, but now takes that z bias and apply it to move it in z. Do that transform, and then we'll pass that as the z. So we're effectively transforming 2 points. One that's the original point, and one that's the original point with a z offset. And then we're using the z buffer value from that one. That allows us to pass the z bias in per vertex so that the 2 base vertices, which are the bottom of the sprite, will get no z biasing, and the 2 top ones will get whatever we want. Does that make more sense? All right, I think that's basically it. Are we going to implement some form of z-buffer in software? Yes, we'll just exactly implement the z-buffer in software. Yeah, and so the key part of that, yeah, like Masilda was saying, just to underscore it, is that effectively what we're doing is we're just transforming the point as it normally would have been if we just specified it normally without the weird z bias. Then we just transform another one and we use with the z bias in, and we use that result as the way that the z buffer will be used. The w is what does the divide. So as long as we use the w from our original default transform with 1.0 going through the pipeline, we'll get the right screen space position. And this z will not affect, because this z is not involved in the divide at all. Remember, z, we don't divide by z, we divide by w. All right, I'm going to go ahead and close it down. Let's see here. And where are we at? So really, our main problem at the moment is not being able to use the sRGB because it means all the colors are wrong, right? Everything's too dark because we can't specify sRGB. So I think we just need to actually move to a graphics card that isn't 7 years old, which maybe I'll have to try and do at some point here. To make things work a little bit more sanely. So yeah, that's what we'll have to do. But everything else seems to be working relatively sanely here. We just need to get those colors fixed so that they're not all messed up. All right. Alrighty. Thanks everyone for joining me for this of a Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along with the series at home, you can always pre-order the game on handmadehero.org. It comes with the source code so you can play around with it. We also have a forum site you can go to if you want to ask questions, a Patreon page if you want to support the video series, a schedule bot that tweets the schedule at you if you would like to know when we're going to be live, and an episode guide for catching up on old episodes. That's about it for this week. I will be back next week when we will, well, I'm not sure what we'll be doing next week, actually, because that's pretty much what we needed to do in terms of the Z-biasing. I think we will probably want to maybe just take some time to clean up and stop using the fixed function pipeline, probably, because we're probably on thin ice there in terms of compatibility. We're lucky that that worked. So just finish transitioning away from that was probably the best idea. So we'll probably take a look at that next weekend, and that is about that. All right. Thanks, everyone. Until next time, have fun programming, and I'll see you on the internet. Take it easy, everybody.